20 articles ago, the premise was simple. The wall between using AI and running AI is gone. This is the proof. A regional management office, a pipeline running a mid-range GPU, 15 years of NOAA storm event records indexed and searchable. A director types a question into a browser. What were the most damaging tornado outbreaks in the Southeast in the last 5 years? 4 seconds later, the answer comes back in plain English. 6 specific events cited by county, date, and damage assessment. Grounded in the actual NOAA record. Nobody called a vendor. Nobody sent data to an external API. Nobody waited for a procurement cycle. The director does not know what is running under that browser window and does not need to. You do. 20 articles of infrastructure reduced to a question and an answer. The wall is gone. You built the door. This is a working language model in production. Models, Part 21. 20 articles of infrastructure. One system. Here's what it looks like when everything works. Section 1. The system you built. This arc is now 21 articles in total. One system. Here is every layer in plain language with the article that built it. The data layer ingests, normalizes, cleans, formats, and chunks 1.2 million NOAA storm event records covering 2019 through 2023. Parts 5 and 6 built it. The output is 400 token chunks with 50 token overlaps stored in data chunked ready for embedding. The embedding layer converts every chunk into a 384 dimension vector using sentence transformers, all mini LM, L6, V2. Part 14 built it. The output is 1.2 million vectors stored in the Chroma NOAA Storm Events collection at the Data Vector Store. The model runs a quantized, instruction-tuned open-weight model with a NOAA domain adapter loaded with PEFT. Parts 7, 8, 9, 10, and 15 established the conceptual foundation and built the adapter. The model runs under Ollama, serving the NOAA Storm model endpoint. The orchestration layer assembles every inference call. System prompt, retrieve chunks ordered by similarity score, conversion story trimmed to a 2-turn window, user query last, all within a 3,500 token prompt budget. Parts 11, 12, and 14 built it. The API layer exposes the pipeline as a fast API REST service with session management, input validation, prompt injection, filtering, and access logging. Part 16 and 18 built it. The human interface layer runs OpenWeb UI connected to the NOAA Storm model on port 3000. Part 18 built it. The process management layer runs the pipeline as a managed system service with automatic restart on failure under systemd, launchd, and NSSM, depending on the platform. Part 18 built it. The evaluation layer established the quality baseline with 140 test cases covering retrieval quality, response correctness, and response consistency. Part 19 built it. The monitoring layer watches input distribution drift, retrieval drift, response quality trends, and infrastructure health continuously, surfacing degradation before users detect it. Part 20 built it. Section 2. A query from end to end. A single query traced through every layer shows the system working as a whole rather than a collection of independently verified components. The director opens a browser and navigates to the OpenWeb UI interface. She selects NOAA Storm Model and types, what tornado outbreaks caused the most fatalities in Alabama between 2019 and 2023? OpenWeb UI formats the query as a POST request to the Fast API endpoint at /query with a session ID assigned to her browser session. The security layer validates the query length at 87 tokens, below the 500 token limit. The prompt injection filter finds no injection patterns. The system passes to the RAG assembly function. The token middleware logs the incoming request with timestamp and session identifier. The RAG assembly function calls the retrieval module. The query is embedded by all mini LM L6 V2, producing a 384 dimension vector. The Chroma collection returns the 8 chunks with similarity scores above 0.6, ranked by score descending. The top chunk covers the April 2021 Alabama tornado outbreak with a similarity score of 0.847. The assembly function calculates the token budget. System prompts at 487 tokens, 8 retrieved chunks at 3,104 tokens combined. Conversation history at 0 tokens for a new session. User query at 87 tokens. Total prompt tokens, 3,678 within the 3,500 token budget. After the 2 longest scoring chunks are dropped to fit, 6 chunks remain. The assembled prompt goes to the Ollama NOAA Storm model endpoint. The fine-tuned model reads the system prompt, 6 retrieved NOAA Storm event records, and the query. It generates a response in 3.2 seconds, citing 4 specific tornado outbreak events with fatality counts, dates, and affected counties drawn directly from the retrieved records. The response includes a confidence assessment of high based on the retrieved context coverage. The response object returns 2 OpenWebUI containing the natural language response, 6 source event IDs, token component counts, and similarity scores for the retrieved chunks. OpenWebUI renders the response in a chat window. The director reads a factually grounded answer, citing the April 2021 outbreak as the most fatal event in the dataset period, with specific county-level detail. The token middleware logs the complete request with prompt tokens, completion tokens, and response time. The access log records the session identifier, token counts, and source event IDs. The monitoring infrastructure captures the query in the daily distribution log. The retrieval metrics fall within baseline thresholds. The infrastructure log records a 3.2 second response time within the 10-second latency threshold. 4 seconds from question to answer. Every layer did its job. Section 3. What this cost. Building this pipeline requires hardware, time, and operational attention. Being honest about those costs is part of what makes this ARC useful. Hardware at the minimum viable tier, an RTX 3060, 12 gigabyte or equivalent, costs between $400 and $500 on the used market in 2026. Power consumption running continuously adds $15 to $20 per month. Total first-year cost at minimum viable hardware is approximately $600 to $700, including power. Build time following this ARC from scratch runs approximately 40 to 60 hours for a practitioner who reads each article, runs each Claude Code prompt, debugs the inevitable first attempt failures, and validates each layer before proceeding to the next. That estimate assumes no prior Python pipeline experience. A practitioner with existing Python experience will move faster through the data preparation and serving configuration steps. Ongoing operational time runs approximately 2 to 4 hours per week for monitoring review, corpus updates when new NOAA data is released, and periodic quality baseline recalibration. That estimate stabilizes as the pipeline matures and the monitoring infrastructure catches issues before they require manual investigation. Section 4. What you actually learned. Following this ARC to completion produced more than a running pipeline. It produced a transferable judgment. You understand why the stack has the layers it has. You know what breaks when a layer is missing because the ARC named each failure mode before it happened to you. You know how to evaluate a model before committing to it. How to design a system prompt that produces consistent output. How to size a chunk for a token budget. How to detect when a deployed pipeline is degrading. And how to use QLoRa to adapt a model to a domain without a research budget. Those capabilities transfer. The NOAA dataset is the through line. The patterns work on legal documents, medical records, financial filings, technical documentation, and every other domain where your data cannot leave your infrastructure, where your use case requires domain fluency a general model does not have, or where the economics of self-hosted inference beat the alternative. Section 5, where this goes from here. This ARC ends here. 3 dimensions are worth naming for what comes next. The pipeline you build is a single user or small team system. Scaling it to serve a larger organization introduces concurrency management, load balancing, model versioning, and access control complexity that belongs in the operations and security series. Series 3 covers that territory. The fine-tuning adapter, built in Part 15, was trained on automatically generated examples. A production, fine-tuned, trained on curated domain examples produced by subject matter experts will outperform it. The fine-tuning article gave you the infrastructure. The data quality work that makes fine-tuning generally powerful is the next frontier. The NOAA pipeline retrieves and generates. It does not reason across multiple inference steps, plan a sequence of actions, or coordinate with other systems. That capability belongs to agents. Series 12 covers the agent's architecture. The LLM pipeline you built in this arc is the inference layer that agents call. The wall is gone. The door is built. What we do with it from here is the work that matters.